all about electric current. Really, that's what I want to talk about. Let me be honest with you. Some of the stuff is kind of magic at this level. If we want to do like algebra-based physics, some of the things it gets kind of complicated, and so you get these superficial equations that doesn't really make sense where they come from. So I'm going to try to do my best to give a summary overall view of the things that you need to know, but still, it's just a start. So there's a battery, and there's a wire. What happens if I take this wire and put it from one end of the battery and touch it to the other end? It gets hot. It would get hot. Okay, but here's another version. What if I do this? Here's a wire with a light bulb, and it's not very bright, so I'm going to turn it on and watch. So here I have a wire going from one end of the battery through the light bulb back to the other end. I have magnets on here to connect it. You see that? Okay, so that's an electric current. Let's think about what happens in a metal. And I want some, here's a marker. Okay, so here I have a metal. And inside this metal we have atoms. Let's say it's iron, okay? Or let's say it's copper. And so those coppers have nucleus with electrons around them. It turns out that in metals, the outer electrons are free to move to different atoms. And so we say there's free mobile charges, and that's what makes a conductor rather than an insulator. So these charges can move around. They end up having no net charge because there's as many positive cores as there are electrons, free electrons, but still the electrons are moving around. They can move around. Now if I have zero electric field inside of there, then they're not going to move, right? Why would they move? And this is what we call static equilibrium, where we have no net excess charges in the center of the conductor. If I do put an excess charge in here, it's going to create an electric field and push charges out to the side, so they'll be on the surface if there are excess charges. That's electrostatics. Now, what if I change this? What if I do apply an electric field inside of here? For some reason, some way I can do that. Well, in that case, all of these electrons are going to experience a force that way. So they're all going to start to move this way. And what happens actually, if you plotted the speed, the velocity as a function of time for one electron, it has a constant force, so it's going to speed up. So it'd speed up, and then it would interact with an atom because it's not free in there. And so it would essentially stop. And then it'd speed up and stop, speed up and stop, speed up and stop. And each time it's different how long before it collides with an atom, collide in quotes. And so this gives some average velocity, and we call that the drift velocity. So if I apply a constant electric field, then these electrons move at an average velocity. Well, they're actually moving this way, in the opposite direction. This motion of charge is what we call a current. So we say a current is the change in charge over the change in time. And it depends on lots of things. It depends on the value of the electric field. It depends on the properties of the metal. In fact, one way we can write this in terms of parameters in there is, let me write this equation, N, E, A, V, D. So this says that the current is proportional to the drift velocity and the area. Okay. So if I have a bigger area with the same drift velocity, I'm going to have more charges flowing, so I'm going to have a larger current. This is the charge per time, not the velocity. Okay. Think about it like water. If I have a water pipe and it expands. Over here, in order to have a constant flow rate, constant cubic, let's say kilograms per time of water. That's like current. Over here, it's not going to move as fast because the area is a lot larger. In order to have the same flow current, that's the same as electric current, except we're dealing with charges instead of mass. Okay, so in this expression, N is the electron density. It's the charge carrier density. How many charges per volume are able to move in this material? E is the value of the charge. If it's an electron, it'd be 1.6 times 10 to the negative 19th coulombs. A is the cross-sectional area, it's this area, and V is the drift velocity. Okay, so this is my definition of current. If Q is in coulombs and delta T is in seconds, then I is in coulombs per second, which is an amp. Okay, so how do you get an electric field in a conductor? Well, one way, you just saw it, was with a battery. This battery creates through a chemical reaction, creates a constant potential difference between the terminals. So when you hook up a wire, it creates an electric current in that wire, and that electric field makes the electric current. Sorry. Okay, let's see. Now let me show you another example. There's a great analogy for electric currents, and that's this, a straw. This is actually a coffee stirrer. So if I take my lungs like a battery and I blow as hard as I can, there's air coming through there. Now what if I take another straw, this is the exact same length straw, but it's wider. You see that? So do I blow through it differently? It turns out yes. If you blow through this, you can get a lot more air going through. Hopefully you can hear that. So these two have different properties. My lungs the same, but I get different amounts of current based on what I blow it through. And the same thing is true for wires, essentially. If I take a longer straw, this one's two straws taped together, what do you think will happen? It's the same as this, the same diameter, but same cross-sectional area, but it's longer. It's hard to measure the air, but let me trust me. This one has more air going through it than this one, even though it's the same lungs, because this one has a larger resistance. It's harder to blow through. A thinner straw has a larger resistance. So we get this property of electrical resistance, and we have a relationship between electrical resistance, electrical current, and change in potential across that element. So we get this. This is actually the definition of resistance. R is the change in potential divided by the current flowing through it. Okay. So if I take this and I was able to blow harder with more lungs, I would get more current. But the ratio of how hard I blow to the current I get would always be constant for this particular straw. Okay. And that's true for the most part for resistors. Okay, but not always. There are cases that does not work. So in this case, if this is in volts, volt per amp, then this gives units of ohms. And that's the Greek letter omega, but we say ohms. You can write it as O-M-S, ohms. And that's the resistance. It's a measure of how hard it is to push current through something. And that's kind of a bad analogy, but you know, we're kind of hand waving here. Okay, so in this case, if I have two metal wires, I have a long one and I have a short one, the same diameter. Oh, short, I said short, shorter. This one would have a higher resistance than that one. So resistance increases with length. If I take a bigger cross-sectional area, this would have a lower resistance. So we have this following definition for resistance. Resistance is rho times L over A, where rho is the resistivity in ohms per meter. Ohm meters. Yeah. And it's a measure of the material properties. So if this is copper, it's going to have a different resistivity than if it was gold or if it was silver. Okay, those different metals have different properties. And then the length of this is L, and the cross-sectional area is A. And if I can use those to find the total resistance. Okay, I told you that this was mostly true, but it's not, because this is not constant. It turns out that the resistivity does indeed change. If I increase the temperature of a wire, here's my wire, if I increase the temperature of this copper wire, then the resistivity also increases. So it's not quite constant. So we can write this as rho equals rho 0, 1 plus alpha delta T. So this is the change in temperature. This is the thermal resistance coefficient, and that's the resistivity at the initial temperature. Okay, but the point is that it does change. Hotter things have a greater resistance, which does have a lot of impacts in real-world applications. Okay, let me tell you about one other thing. So here is a battery. This is 1.5 volt battery. This wire has a resistance of, let's say, it's probably 1/10 of an ohm, but let's just say it's 1 ohm. It's not 1 ohm, it's lower. Okay. If that's the case, and I say I apply a 1.5 voltage across this, and it's 1 ohm, 1.5, and that's 1, then the current should be 1.5 amps. And 1.5 amps is kind of high. Okay, but you don't get 1.5 amps out of this battery. It's not gonna be that high. And there's mathematically that doesn't work, because real batteries have something called internal resistance. So if I pretend like I have a battery, we could actually model a battery like this. So this is the plus side and this is the minus side. Inside we have actual ideal battery of 1.5 volts. And then we have a resistor called R internal resistance. And so what happens is if I put a 1 ohm resistor here, then the total resistance is not 1 ohm. Let's say this is 10 ohms internal resistance. The total resistance is 11 ohms. Okay. Now, if I put something, some huge resistor over here, 1,000 ohms, then the total resistance would be 1,010, which is approximately 1,000, so you don't really notice it. So if you're using low current situations, you don't even notice that internal resistance. Okay. Okay, now that's just a bare introduction to electric current, voltage, and resistance. The next thing is to talk about the, deuce circuit problems, but I'll save that for another video.